Assalamualaikum warahmatullahi wabarakatuh. Welcome back to the lecture. Today we're going to cover the topic thin films deposition. So thin film deposition is a technique where we apply very thin film of material between a few nanometer to about 100 micrometer or the thickness of a few atom on a substrate surface so that we can coat it and onto a previously deposited coating to form layers. So why thin film is used in the semiconductor fabrication? First is to maintain the surface uniformity, and it is also a simple fabrication where manufacturing require less material. It also reduce light absorption material, and also strange electrical, optical and mechanical properties can be improved via the thin film deposition. Thin film deposition technique has been used in many applications, for example in microelectronics, optic, magnetic, resistant coating, micromechanics, and etc. So better result in this area depend on the selective and the control deposition that we use. And then there are vast number of deposition method available. Some of them we are going to go through in this lecture, and all methods have their specific advantage and also disadvantages based on the substrate, source of material, thickness of deposition film, and many more of parameters. So this make it very difficult to select the best technique for any specific application, and some of these methods are discussed in this lecture. Thin film deposition process can be classified into four techniques. Okay, so they are PVD, CVD, doping, and also oxidation. Some of the topic we already gone through in general in IC fabrication. So in here we are going to look in detail on the process of the PVD, CVD, doping, and oxidation, and what are the details and parameters inside the process. Deposition technique can be classified into four category or processes. Okay, so it depends on the type of how the ion or the substrate is being deposit. Okay, so one is a glow discharge process. Under it there are sputtering and plasma processes. Gas phase chemical processes, we have low pressure CVD, metal organic CVD, laser induced CVD. And then for liquid phase chemical process, we have electroplating and spin on techniques. And the last techniques is vacuum evaporation technique. So under this, they have conventional vacuum evaporation, molecular beam evaporation, molecular beam epitaxy, and reaction evaporation. Okay, so this one involve evaporation in vacuum condition. So if we classify the deposition techniques into physical vapor deposition and chemical vapor deposition, so under physical vapor deposition or PVD, there are vacuum evaporation techniques, sputtering, and also spin coating. For chemical vapor decomposition, we're going to cover the APCVD, LPCVD, and PECVD. Okay. So chemical vapor deposition involve reactive carrier gases. So transport precursor of desired material to the substrate surface. So gas is carried. Gases will react with other gases or decompose to produce a stable reaction product and deposit on the substrate. So after the reaction, and then it will start to deposit on the substrate. So it is a most versatile deposition techniques because it involves a wide range of chemical reaction, reactant, and also it can be used for many applications. In CVD process, depend on the process parameter, pressure, temperature. The method can be divided in different methods, so which layer differ in density and coverage. So if the growth on the horizontal surface is high, or vertical spaces as high as vertical spaces, so meaning that horizontally and vertically it is the same, so the position is confirmed. Okay, so the conformity is calculated is represented as K is the ratio of the vertical and horizontal growth. So the equation can be K equal to RV over RH. So the thickness of the position, the layer on the vertical and horizontal. Okay, so if the position is not ideal, the conformity will be less than 1. For example, RV over RH equal to 1 over 2, which is around K equal to 0.5. So this one showing that it is not ideal. So a high conformity can only be achieved using the high process temperature. So here the example on how the conformity for when the conformity is 1, the K value, if you can see, the distributions of the layer is the same. Okay, so when it is not ideal, so it become a certain part become quite thin and another part is thick. So if there is an inhomogeneous deposition, they will look at the third picture. Atmospheric pressure CVD or APCVD is a CVD methods where the normal pressure or atmospheric pressure is applied during the process of deposition of dope and undoped oxide. So the deposited oxide has a low density and the coverage is moderate due to the relatively low temperature. Example for the atmospheric pressure CVD process is a process where gas silane SiH4, which highly diluted with the nitrogen and oxygen used, and then the gases are decomposed at the thermal of 400 degrees Celsius to 450 degrees Celsius, and then in this one will react with others to form a desired film. So you can see the chemical equation below, where SiH4 will react with the oxygen and also to form the um, silicon oxide and also the hydrogen. So this one is performed at the temperature of around 430 degrees Celsius and pressure around 105 Pascal. So if we add ozone O3, it can cause a better conformity because it will improve the movability of the accumulated particle into the process. And then the outside is for this operation is a little bit porous and electrically unstable. So in order to improve this process, it can be densified by using a high temperature process. The next process is low pressure CVD. So LPCVD is a vacuum process. So you have to use vacuum environment in this process. Thin film of silicon nitride, silicon oxynitride, silicon oxide, and also tungsten can be created in this process. So for LPCVD process, it enables a high conformity, which almost 1, so which is quite good. So this is because of the low pressure of 10 to 100 PA, which is atmospheric pressure is around 100 PA, right? So which lead to a non-uniform movement of the particle. So the particle will disperse due to the collision and cover vertical spaces as well as the horizontal. Okay, so the conformity is supposed to supported by the high temperature. So compared to the APCVD, this one is double the temperature, which is around 900 degrees Celsius. So compared to the FECVD, the density and stability will be high compare is we want to compare it. So here is the diagram showing the low pressure CVD process. If you can see, the wafer is being arranged on the tray, and then there will be gas inlet that will supply the gas into the chamber, the vacuum chamber. So then the reaction will happen in this chamber where it will create the type of layer of thin film that we want to create. For example, in here we have we can create Si3N4, SiON, SiO2 and tungsten. Okay, so the reaction equation can be seen in the equation below. So you can see that how the Si3N4, SiON, SiO2 and tungsten is being created. So the next process of CVD is plasma enhanced CVD. So in this process, what we call as PE-CVD, it take place at the temperature of 250 to 300 degrees 350 degrees Celsius. So due to this low temperature, the process gases will not be able to decompose thermally. So that's why frequency voltage is supplied so that the gas transform into plasma state. If you can remember the etching topic previously, so the same method is used where the gases is transformed into plasma. Okay, so then when it is transformed into plasma state, it will become very energetic and disposed on the surface. So because of the metallization such as aluminium that cannot be exposed to high temperature, so the PE-CVD is used for the silicon oxide and Si3N4 deposition on top of the metal layer. So instead of the silent gas previously mentioned in the atmospheric one, so in here SiH2Cl2 silane is used because it can be decomposed at lower temperature. But in this PE-CVD, the conformity is less than the LP-CVD, so it is around 0.6 to 0.8, but the position rate is much higher, which is around 0.5 micron per minute. For the physical vapor deposition or PVD, physical vapor deposition is one of the vacuum coating process in which the film of the coating material is usually deposited atom by atom on a substrate by condensation from the vapor phase to the solid phase. The first process for PVD is evaporation deposition. So in evaporation deposition, there will be material to be deposit is heated in high vacuum chamber. So this one to minimize this process is performed in vacuum condition in order to minimize the collision in source atom. So that's why it's called vacuum deposition. Okay, so this heating process is performed by resistive or e-beam source. So that's why we give the name is thermal evaporation and also e-beam evaporation. So the surface interaction are physical and it can be very fast, which is around bigger than 1 micrometer per minute. So high sticking coefficient leading to poor conformal coverage due to the significant shadow. But this also make evaporation the most popular thin film deposition for nanofabrication, which use lift-off process. So the deposition rate is determined by emitted flux and also by the geometry of the source and the wafer. This kind of evaporation is not widely used in the industry, but as sputter deposition, but it is used in the R&D purpose, so it's very important method to be used. So thermal evaporator is used for material which vapor pressure can be reached at 1600 degrees Celsius to 1800 degrees Celsius or less than that. So the common evaporant is like gold and then silver, aluminium and many more. So in here, in this process, the material will be placed on the crucible here. So if you can see the yellow part, this one, okay, so the metal will be placed inside here and then it will be heated. So in here, the heater can be tantalum or it can be tungsten. Okay, so this the heater will give heat and make sure the metal to evaporate. So the metal will evaporate up here, and then it will be deposit on the surface. So but the problem is there will be shadow. So this one, the SC area usually is not covered. Okay, so that's one of the problem with this kind of process. Okay. Another alternative for the evaporator is by using the electron beam instead of the crucible. Previously, we see that the metal is placed in the crucible, right? But in here, the e-beam is used to evaporate the part. So the e-beam is created from the hot filament, and then it goes is here, and then make the material in here to vapor to the substrate. Okay, so compared to the thermal process, electron beam will allow a precise growth. Okay, so then because of the bad edge coverage, both methods are mostly used for the backside deposition for final contacting. Here is some comparison between the thermal evaporator and e-beam evaporator. So thermal evaporator is simpler compared to the e-beam evaporator, but and used at a large scale. So the filament is different. So this one, it can use tungsten and also Ta filament as a heater. So filament can produce produce current around 200 to 300 ampere. So and substrate will expose to the infrared or visible ray. So in here, in thermal evaporator, there is contamination from heated board. Okay, for e-beam evaporator, more complex, and but it can be used for almost kind of the material. Compared to the thermal evaporator, e-beam evaporator have less contamination and heated to wafer, and exposed to substrate to secondary electron radiation, and X-ray can be generated by the high voltage electron beam. Sputtering is the process where basically is discovered as an etching process in 1892, but then it is developed into the thin film deposition technique in 1920 by Langmuir. So sputtering process involves the ejection of surface atom from an electrode surface. So what happened is the gas, for example, in this picture, if you can see, the argon gas is supplied into this one. So the positive ion of argon will go to the sputtering target. So then it will make the metal target metal ion to deposit towards the substrate here. So this one, the argon will bombard this part, this metal to the substrate. Okay, the sputtering produce a vapor of electrode material and used to deposit the thin film. So more basically, it can be used for etching process, for example, by to clean the surface or pattern delineation. The last process is spin coating. So spin coating is the same process where we apply the resist on the substrate, which is the wafer. So where the material is placed on the wafer, so then the spinning take place in order to make sure the only thin layer of material is being deposited on the surface of the wafer, and then let it dry so that it stick to the wafer surface. So that's the end of our class today. We will cover the next topic, which are oxidation and also doping, in the next class. Thank you for listening. Assalamualaikum.